Well, hello everybody. It's Monday, April 20th, and I'm sitting out here on my deck. The wife's down in the basement COVID bunker. She's working out on the rowing machine, so too much noise down there while she listens to her Motown music. So I'm out here in the backyard, and so where are we at today? Well, we're in Chapter 7. This is the second lecture of Chapter 7. And I imagine we might only have one more lecture out of Chapter 7, so Wednesday could be the last lecture, and then after that, I'll continue to post some homework solutions as videos and so on, so you can see the solutions to those. But also, I think I've been able to go a little bit faster with the lectures by videotaping, not so much messing around when we're in the classroom, passing homework out and all that kind of stuff, and telling jokes and stories and so on. So it's been pretty dry, I imagine, listening to these lectures. But I guess the good news is it allowed us to cover the material a little bit faster. So I imagine next week for sure we won't have any more lectures other than just going over the homework assignments, and this will give you a little more time to get caught up on homework. Maybe go back and revisit some of the videotapes of the lectures, and also ask me any questions and so on that you might have. And just remember that our final exam is on that Friday of exam week, so I'll have more about that in the coming days or so. But keep an eye on the blog. I'll post information on the blog about the final exam. But I think it starts at 12:30, so make sure on that last Friday of exam week that you prepare yourself for 12:30 exam for the start of that. So that's about all I have right now to talk about, so we'll get started with the next lecture. Hope you guys are all doing well, stay safe, and stay well. Okay, let's take a look at the solutions for homework 15. The first problem was problem 613, and we're given a whole bunch of properties about a transport of a solute across a membrane, and we're told to find the effective diffusivity. So in this particular case, we can assume a temperature of 37 degrees C or some other reasonable temperature. We're also told that the pores are straight, so that would tell us that the tortuosity is equal to 1. And then we convert the radius of the pores to centimeters, so that calculation is shown there. And then next we can use equation 535 to determine the solute diffusivity for the given molecular weight of the solute material. So we do that calculation here, and we get this value of the diffusivity. And then from the solving for the radius of the solute, we can go through and do that calculation right here for the molecular weight of 35,000. We get a radius of the molecule of 2.403 nanometers. And then next we solve for the pore diffusivity using equations 6.8 and 6.13. That calculation is shown next. So here's the equation that you would use, and you'd pop in the diffusivity that we calculated above. Here's the radius of the molecule. This is the radius of the pores, and you have to carefully evaluate this particular value of the omega r from the Rankine equation, and that gives us a d pore of 9.65 times 10 to the minus 8 square centimeters per second. And then from equation 6.8, we know that the membrane diffusivity, which we call dm, takes into account the partitioning from the bulk solutions to get inside the pore. So that's where we use Ferri's equation. Here I'm just using the solute radius and the pore radius in nanometers, so we get a K value of 0.16. And then at the top of the next page, with that membrane diffusivity that we calculate here, 1.54 times 10 to the minus 8 square centimeters per second. We also know from the relationships that we developed in Chapter 6 then that the effective diffusivity for the entire membrane, which takes into account the porosity of the membrane, would then be epsilon times the membrane diffusivity, and that calculation is shown right here. So we end up with a value then of 6.15 times 10 to the minus 9th square centimeters per second for the effective diffusivity. Now the next problem is 615, which is shown here. And in this case we're told that the pores have a tortuosity of 1.5, and once again we're going to calculate the effective diffusivity of the solute for this particular membrane. The first thing you do is convert the radius of the pores to centimeters, so that comes out to be 7.5 nanometers. Next, calculate the molecular weight from the solute radius, and that's shown here. So the molecular weight calculation based on the solute radius that's given in the problem. So we end up now with a molecular weight of 39,400 grams per mole. And then we would use equation 535 with this molecular weight to calculate the solute diffusivity at 37 degrees C, which is shown right here. And then we go back into equations 6.8 and 6.13 to first calculate the pore diffusivity, which is shown right here. So this busy calculation here gives us a pore diffusivity of 1.94 times 10 to the minus 7 square centimeters per second. And then to take into account the partitioning from the bulk solution into the pore, we would multiply that by the partition coefficient given by Ferri's equation, 6.1. So the K comes out to be 0.444, and that tells us then that our membrane diffusivity is 8.61 times 10 to the minus 8 square centimeters per second. And then once again, if we multiply that membrane diffusivity by the porosity of the membrane, we calculate the effective diffusivity of the membrane for the solute of 3.44 times 10 to the minus 8 square centimeters per second. Next we have problem 620. We have some data given from Bawa's paper for the fractional release of a solute from a membrane. And basically the solution for the fractional release is given by equation 633 that we obtained by separation of variables. And we also showed in that section that if you go with a short contact time solution and your fraction release is less than 0.4, you could do a linear regression of the data points in this region here, and then by equation 639, once you find the slope, you can evaluate the effective diffusivity. And then for the data that lies above a fractional release of 0.4, you can use equation 641, which is another linearized equation that allows you to find the effective diffusivity. Now some people in the homework, what they did is they forgot this little distinction, and they would just regress over all the data using equation 639, which doesn't give you a bad answer. I might not have taken anything off for that. I kind of just went along with the flow on that one. But you know, you have to really be aware that these equations have limitations. Now up here, if you use equation 633, which has that infinite series summation, you can actually just do a nonlinear regression and search for the best value of the effective diffusivity that minimizes the error between the data and the model prediction given by equation 633. And my student from a few years ago, Robbie Aris, yeah, he graduated in 2017, and he's now a third-year medical student here at the University of Toledo. He was a much better MATLAB programmer than me, and he actually figured out how to write a MATLAB program that would do the nonlinear regression, and this is his program. I'll just scroll through it slowly here. If you're really interested, you can copy it down for yourself. But he worked through all that and was able to solve it. And that's right down in here. This is equation 633. Right in here is where the actual model equation is that he uses to find the value of dE. So when he did all that, he ends up with a value of the effective diffusivity of about 5.3 times 10 to the minus 6 square centimeters per hour. And on the next page here, you can see a comparison generated by his MATLAB program. Here's the FR value over here. Here's the time in hours. The boxes are the experimental data, and the solid line is the best fit of equation 633 to that data with the optimum value of dE, which shows how well this diffusion theory that we've been developing fits actual release data for a device. And then the last problem in this homework assignment was problem 624, and you're given a bunch of properties about a membrane, and you're told to estimate for that membrane the solute membrane permeability, which is defined by equation 615. So remember, permeability of a membrane is really the effective diffusivity given by all of these terms divided by the physical thickness of the membrane. So the diffusivity of the solute can be found from equation 535 using the given molecular weight. So that gives us this particular diffusivity. Also from equation 541 we can find then the molecular radius of the molecule, and then what we do is just go in and estimate the various terms in here. We're also given some information that allows us to calculate the tortuosity as well. So when you do the calculations given the data in the problem, you'll find that the lambda value, which is the ratio of the molecular radius to the pore radius, is 0.16. And using that lambda value, you can go to figure 6.4 or use equation 612, and you can find that your K omega R is 0.474. And substituting these answers and other values given in the problem in the equation that defines PM, you can calculate a membrane permeability of 4.6 times 10 to the minus 6 centimeters per second, where the tortuosity of the membrane is also given by the information that's provided. So the tortuosity of the membrane in this problem is 1.3. Okay, in the last lecture we started chapter 7, and we started to talk about the diffusion and reaction of oxygen in tissue, and we focused, one example was a spherical collection of cells, and we saw data for that for the Brockman bodies, which showed that oxygen really cannot diffuse very far into tissue. And anyways, we solved for the diffusion and reaction within the Brockman bodies and showed how we could extract from data the oxygen consumption rate of the cells. And then we started to talk about hemoglobin and oxygenation of tissue via the hemoglobin molecule, which we showed can carry up to 4 oxygen molecules. And the transport of oxygen, say between blood and tissue, occurs because of a difference in the concentration of the oxygen. And the one thing we have to be aware of when we're talking about oxygen transport is that we use the PO2 of oxygen and the concentration of oxygen synonymously. So you have to be fluent in being able to convert back and forth. Sometimes people talk about the oxygen partial pressure, other times they'll talk about the actual oxygen concentration, and the relationship between those two are given by what's known as Henry's law. And the Henry's constant we denote by capital H, and we put a little oxygen or other decoration on there. And the Henry's constant for blood at 37 degrees C, a pretty good number for that is 0.74 millimeters of mercury per micromolar. So micromolar is our oxygen concentration, and our PO2 is expressed in millimeters of mercury. And remember that the PO2 of a gas is just the mole fraction of oxygen in the gas times the total pressure. So for air at atmospheric pressure, the maximum PO2 would be about 160 millimeters of mercury. And then we talked about the oxygen hemoglobin dissociation curve, which is very important in what we're going to be talking about today as well. And that's shown as figure 7.4. And what we have over here is the fractional saturation of the hemoglobin plotted against the PO2. And remember the normal physiological range of PO2 of blood in your body, venous blood's down here about 40 millimeters of mercury, and arterial blood is up around 90 to 95 millimeters of mercury. And since there's about 150 grams of hemoglobin per liter of blood, and each hemoglobin molecule, when saturated, can carry 4 oxygen molecules, then the oxygenated hemoglobin at saturation is 8,800 micromolar. So if for a given PO2, if you come over here and read off the fractional hemoglobin saturation, you would take that number and multiply that times the 8,800 to find out how much actual hemoglobin you have at that particular PO2, as shown by this calculation right here. So that's where we ended up the other day, and we'll continue on from there. So a couple things we want to first talk about would be the oxygen levels that are found in blood, and that's summarized up here, and I've walked you through most of what's in this paragraph up here, but there's lots of information that's really important, and a lot of that information is also summarized down here in this table down here, table 7.2, which is called the oxygen levels in blood. So these are nominal values. Typical arterial blood would be 95, would have a PO2 of 95 millimeters of mercury. Venous blood would be 40 millimeters of mercury. And then if you took the 95 millimeters of mercury and divided that by the 0.74, you can see you can calculate the dissolved oxygen concentration, which I get here is 128.4 millimeters of mercury, and I probably just rounded it off to 130 over here. And then as oxyhemoglobin, the 8,500, what you would have to do to get that value, the oxygenated hemoglobin arterial, that's what the A is up there for, would be the fractional saturation from figure 7.4 at 95 millimeters of mercury times the 8,800, and this fractional saturation would be 0.965, which gives the 8,500 millimeters of mercury. And if we compare these two numbers then, both which are calculated at 95 millimeters of mercury, you can see that the amount of oxygen being carried by the hemoglobin is many fold bigger than the amount of oxygen that's actually dissolved in the blood. And similarly, you could do the same calculations over here for the venous, and then down here in the little subheading, you can see this table summarizes the oxygen Henry's constant, the saturated hemoglobin value, and something that's called the P50 and the N value that we'll be deriving next. But the P50 value is the value of the PO2 where the oxygen or the hemoglobin is half saturated. So this is the level of 50% saturation. And if we were to go back and look at the hemoglobin, the oxygen hemoglobin dissociation curve, figure 7.4, you can see from the graph that at 50% saturation that value is about 26 millimeters of mercury. So the P50 value is 26 millimeters of mercury is a good number for that. Now what we'd like to do at this point, especially for calculations that might involve a computer, is we'd like to be able to have an analytical expression to describe the saturation of hemoglobin as a function of PO2. And this guy Archibald Hill back in 1913 used a mass action type reaction rate law to describe the binding of hemoglobin with oxygen. So hemoglobin and oxygen forms oxyhemoglobin, or you could think of it as oxyhemoglobin dissociates to form hemoglobin and oxygen, free oxygen molecules. And this is a reversible reaction, and if you go through and just apply standard mass action rules for chemical kinetics and treat this system at equilibrium, you can come up with an expression which is shown on the next page in the box, and you can develop this expression, equation 714, which is very important because it allows us then to describe the fractional saturation of the hemoglobin molecule with oxygen in terms of the PO2. And the curve fitting parameters are the P50 value, which we just talked about, and the value of N. Now N is not going to be equal to 4 because this is just a simple model of the process. So N comes out to just be a curve fitting parameter. In this case it comes out to be around 2.3, something like that. And we'll show how we can find the values of the P50 and the value of N by fitting data like what we saw earlier in figure 7.4. So this is called the Hill equation, and if you know the P50 and the value of N for a given PO2, you can just go in there and do the calculation. And if you look at this equation, it looks a lot like, Michaelis-Menten kind of equations that we've talked about earlier. If you've taken some biochemistry, you know that the binding of oxygen with hemoglobin is a cooperative binding, and this type of equation is what you probably saw in those cases to describe cooperative binding. So in order to fit data to it, you can actually rearrange this equation, and you can show that you can get this linear form of the equation right here. So by manipulating it and then taking the natural log, you can find out that if you plot the natural log of the hemoglobin saturation fraction as a function of the natural log of the PO2, that the slope of that plot would give you the value of N, and the intercept, from the intercept and knowing the value of N, you can find the P50 value. And that's what's shown in example 7.2. What I did here is just carefully read off the oxygen PO2 levels from the graph and the corresponding fractional hemoglobin saturations, and then applied the transformation given by equation 715. And when you do that and you do the linear regression, you get the results that are shown at the top of the next page here. And we find that the P50 value is in fact 26 millimeters of mercury, which is what we were able to just get from looking at the graph itself, and the value of N is 2.34. And then here's a comparison plot between the actual data that we used, shown by the square boxes, and the dashed line is the prediction of the Hill equation. So you really have a choice. I mean, if you want to quickly find the degree of saturation of hemoglobin, you can use the figure and easily read values off. If you're doing more involved calculations and you're writing a computer program, then you could use the Hill equation and use the values of P50 and N that we just found in this example. Now there are some other factors that affect the binding of oxygen and hemoglobin, and that's discussed in this next section and shown on this curve here in figure 7.6. Once again, we got the fractional hemoglobin saturation versus the PO2 on the abscissa. The solid line would be your normal values of the hemoglobin oxygen binding, and then there's various things here that can happen. So example, if you had an increase in hydrogen ion concentration, which would lower the pH, or an increase in CO2 or increased temperature, what happens is that this curve actually would shift to the right. And the net effect of that, what that means then is that, say, if you were at a given PO2 of 50 millimeters of mercury, you can see if the curve shifted to the right, that effectively unloads oxygen because the degree of saturation is decreased by any of these things happening. And this is very important, like in exercising muscles and so on, you produce a lot of lactic acid locally, which lowers the local pH a bit. That shifts the equilibrium curve to the right and helps unload oxygen from the hemoglobin. Likewise, the increased CO2 levels in the blood during exercise have the same effect, and even the increased temperature. So these are all physiological responses that happen in your body as a result of exercise that facilitates the unloading of oxygen. So with that background, what we want to talk about next is how this affects tissue oxygenation. How do we actually use this to figure out how much oxygen has been unloaded from blood and how much oxygen is passed into the tissue. Now there's a couple of fine points right here. We're going to do a simple mass balance, and there's some things that I want you to be aware of. We're going to let capital V sub T represent the volume of the tissue space, which includes the capillaries, and we'll let lowercase q be the tissue blood perfusion rate. So that's going to be the total blood flow to that volume of tissue divided by the volume of tissue. And that's going to have units of like cubic centimeters of blood per cubic centimeter of tissue per minute. And then we'll let lambda oxygen with a prime on it represent the tissue oxygen consumption rate, once again in micromolar per second, on a total tissue volume basis. So what that means then is this gamma prime oxygen is equal to our gamma oxygen that we talked about earlier, which is based on the actual volume of the cells, and the relationship between the two we'd have to take this value of gamma oxygen times the cell volume fraction in order to find the lambda prime. Now C oxygen is going to represent the dissolved oxygen concentration in the blood. And remember, as I mentioned before, it's only the dissolved oxygen concentration that drives the mass transfer. That's your driving force. The amount of oxygen bound to hemoglobin is just a local source or sink of oxygen, depending on what's happening with the PO2. So gamma prime HBO, that's going to represent the concentration of oxygen in the blood that is bound to hemoglobin. And C bar oxygen with a bar on top would represent the concentration of oxygen in the tissue space. So if we do a mass balance around a volume of tissue, as shown up here on the next page in this little diagram I got, this here would be a volume of tissue that we're interested in, and we would know the flow rate of blood into the tissue and the flow rate of the blood out of the tissue would have to be the same, and that total blood flow rate Q would be equal to the blood perfusion rate times the volume of the tissue. So VT, remember, is the total volume of the tissue, which includes the cells, the interstitial fluid, the capillaries, and all of that. So if we think about this, basically the total oxygen consumption by this volume of tissue has to equal the loss of oxygen by the blood flowing into the tissue and out of the tissue. So if we take the amount of oxygen in the incoming blood, subtract off the amount of oxygen in the blood leaving, that difference would have to equal this quantity right here, which represents the rate of consumption of oxygen by the tissue. And we can then cross out the VTs, because the actually the way it's going to work out is that the the amount of the tissue that we're talking about gets crossed out, whether you're talking about it here or over here in terms of the blood convection term. So these VTs would cancel out, and when you put in the amount of oxygen in the arterial and venous blood, you end up with what we call equation 718. So 718 then would be our basic material balance equation for a volume of tissue, which tells us then that the oxygen consumption rate based on the total volume of the tissue is equal to the blood perfusion rate times, and now what's this quantity in brackets? And what you see now when we talk about arterial blood, we have to ask ourselves how much oxygen is dissolved in the blood and how much oxygen is being carried by the hemoglobin, minus then the amount of oxygen in the venous blood. So the distinction now that we have to make is we have to include the amount of oxygen bound to hemoglobin, and you have to remember that the amount of oxygen dissolved and the amount of oxygen bound to hemoglobin depends on the local PO2 or the local value of the dissolved oxygen concentration. Now in the next section I just talk about nominal tissue oxygen consumption rates. We could take equation 718 for the oxygen consumption rate of tissue, and if we knew the blood perfusion rate and we know the typical arterial PO2 and venous PO2, we could then take this equation and solve for oxygen consumption rates of various tissues as a function of their blood perfusion rate. And down here in table 7.3 I just summarize blood flow to different organs and tissues under basal conditions, so from the brain all the way down to adrenal glands and so on. Here's the percent of the cardiac output that those organs get. Here's the milliliters per minute, and then here we've normalized the blood flow to 100 grams of tissue. And in example 7.3 it says calculate the oxygen consumption rate in micromoles per second using nominal values for the blood perfusion rate and the arterial and venous PO2 levels. So if you let's see, if you go to table 7.3, just in a ballpark sake of argument sense, a nominal tissue perfusion rate in tissue is on the order of 0.5 milliliters of blood per cubic centimeter of tissue per minute. So we'll use that as our Q in equation 718, along with the PO2 of arterial and venous blood. And as shown at the top of the next page, we can then calculate a nominal oxygen consumption rate of tissue. And you got to remember though that this value varies for all the different types of tissue in the body. So this is more just for illustrative purposes. But if you go to equation 718 and you put in that 0.5 nominal blood perfusion rate. If you go to the table where we had the total amounts of oxygen present in arterial and venous blood, pick those guys off, and then just be careful and crank through the unit conversions, recognizing that we're talking about volumes of blood and volumes of tissue, so you have to be careful in your calculations in that regard, as I show here. But when you crank it all out, then you find that a nominal oxygen consumption rate of tissue in the body is about 18 micromolar per second. So you could, basically say, just ballpark, if someone asked, at what rate is oxygen being consumed in the body's tissues, it's on the order of 20 micromolar per second. We'll see, though, later on. We'll look at like chondrocytes. There's some tissues in the body that have very, very low oxygen consumption rates. So, this range could go all the way down to 0.05 or 0.01 micromolar per second, depending on the oxygen needs of the particular tissue that you're talking about. Now, in another type of calculation that can be done is illustrated by equation 719. And in this particular case, suppose you knew the perfusion rate and you knew the oxygen consumption rate of your tissue. You know your arterial blood's coming in at 95 millimeters of mercury. And now what you want to find for these conditions is the exiting venous conditions of the blood. What's the PO2 of the blood coming out? So everything on the right-hand side of this equation would be known. The problem is that you'd have to put Hill's equation in right here for the amount of oxygen bound to hemoglobin, which depends on the unknown PO2 or the unknown venous dissolved oxygen concentration. So this calculation really gives you a nonlinear algebraic equation, which you'd have to solve using some kind of a root solving technique in order to find out what that is. And I talk about it in this section here. You can read through that on your own, and it continues over on to the next page here. And I kind of lay out what the algorithm would look like. Here's your Hill equation that you would write in terms of the unknown venous dissolved oxygen concentration. So equation 719 ends up looking like equation 721. So you can see now everything on the right hand side you would know. Everything on the left hand side only now depends on the unknown dissolved oxygen concentration, that you could then solve this equation for the oxygen concentration in the venous blood. And once you have that oxygen concentration in the venous blood, as I show over here, once you have that venous concentration of the dissolved oxygen in that blood, then you can multiply that by the Henry's constant, and that would give you the PO2 of the venous blood. And this is all talked about in greater detail in example 7.4, which you can read about on your own. So what we want to do is we want to apply this to some typical problems that arise in biomedical engineering in terms of the design of devices and so on. And that's what section 7.8 is about. So what we want to do now is take what we know about mass transfer, the role of hemoglobin, and so on, and talk about oxygen transport and blood oxygenators, bioartificial organs, and tissue engineered constructs. Now, in one type of bioartificial organ proposed for the treatment of diabetes, for example, the therapeutic cells such as the islets of Langerhans or other insulin-secreting cells that may come from genetically created insulin-producing beta cells, you take those cells and you sandwich them between two perm-selective membranes that are surrounded by vascularized tissue or adjacent to a polymer matrix material that has been vascularized by the host. Now what this perm-selective membrane does is that it allows the key small molecules like oxygen, nutrients, and the therapeutic agent like insulin to be readily transported across the membrane. However, the components of the host immune system cannot cross the membrane. So that's what we mean by bioartificial organs, is they usually employ immunoprotection of the transplanted cells. In tissue engineering applications, cells are produced within porous polymeric constructs that in many cases can be represented as thin discs. In these applications, key nutrients are brought to the cells primarily by diffusion, and in most cases the critical species that affects the design of these devices is your ability to transport oxygen. And then the following discussion, we're going to look at an oxygen mass balance for blood oxygenators, and then we'll focus on calculating the oxygen gradient in thin planar or one-dimensional discs that contain cells with the goal of providing sufficient oxygen to the cells. So there's quite a bit that we're going to be talking about in the following pages in the book, and I'll try to keep it organized for you. And what we'll do is we'll get started first talking about oxygen mass balance for a blood oxygenator. So in the little drawing down here at the bottom of the page, in its simplest form, we could think of the blood oxygenator as just a box, and we would know these would contain hollow fiber membranes, and the blood would be typically flowing on the outside of the fibers, and oxygen is flowing within the fibers, and the goal is to raise the PO2 of the incoming blood to a higher value over here. If this is a blood oxygenator being used to keep a patient alive during say open heart surgery, the incoming blood might have a PO2, venous blood PO2 of 40 millimeters of mercury, and the goal is to raise it up to 95 millimeters of mercury. So this device has to replace the pumping function of the heart as well as the oxygenating capability of the lungs. So, you know, for basically the actual mass transfer design of this is described in later chapters of my book, where I talk about artificial organs like blood oxygenators. And what we want to do here is just do a basic material balance, for example, to calculate what the mass transfer rate of oxygen would have to be in order to raise the oxygen from some incoming level to some outgoing level there. So our basic oxygen mass balance for that oxygenator could be written as shown here by equation 722. The difference between the oxygen level and the exiting blood and the entering blood times the blood flow rate would have to equal the oxygen mass transfer rate, or the amount of oxygen that would have to be delivered. And that's illustrated in example 7.5. And here we have blood travels through a membrane oxygenator at a flow rate of 5,000 milliliters per minute. The entering PO2 of the blood is 30 millimeters of mercury, and the exiting blood PO2 is 100 millimeters of mercury. Calculate the amount of oxygen transported into the blood in micromoles per second. So at the top of the next page, we show the solution to this problem. First, we need to find the amount of oxygen that's dissolved in the blood at 30 millimeters of mercury, and then at 100 millimeters of mercury. And this can be found from Henry's law given by equation 7.1. So here's our rearrangement of Henry's law to solve for the dissolved oxygen levels in the incoming and outgoing blood. So we take those respective PO2s of 30 millimeters of mercury, 100 millimeters of mercury, divide those by the Henry constant, and that tells us the dissolved oxygen concentrations in those respective blood flows. Then the amount of oxygen bound to hemoglobin can be found from figure 7.4, or you could use the Hill equation. At 30 millimeters of mercury, the hemoglobin saturation from that graph looks to be 0.58, and at 100 millimeters of mercury it looks to be 0.97. So therefore we would multiply those values by the saturation level of oxygenated hemoglobin, which is 8,800 micromolar, and that then tells us how much oxygen we have being carried by the hemoglobin. So now we go back to the previous equation, our material balance equation that we had earlier, right here, and we plug in the various numbers, go through and calculate all the units, and you can see that our oxygen transport rate would have to be 293.9 micromoles per second. Okay, so yeah, I'm going to make this kind of a shorter lecture today, and what we'll do on Wednesday is we'll come back and start talking about oxygen transport in planar bioartificial organs. And we'll see you on Wednesday.